In the murky depths of the ocean, what insidious entities dwell? Lampreys. No, not the ones that hitch a ride on fish. I'm talking about the Lockheed Martin Lamprey, a next-generation naval drone that activates remotely at extreme depths, deploying integrated docking anchors to hitch a silent ride on ships and submarines. By clinging undetected, it conserves energy while traveling hundreds, even thousands of miles to its mission zone. And what's really amazing is that while it's attached, onboard turbines harvest power from passing water. That capability ensures it arrives fully charged and ready to operate. Once released, its open, payload-agnostic design supports everything from torpedoes and electronic warfare gear to acoustic decoys, intelligent sensors, and even launchers for aerial drones. Multiple units can work together, settling silently on the seabed to watch, wait, and strike when commanded. It links the seabed to space with an integrated communications relay, keeping everything connected from the ocean floor to orbit. Instead of risking crewed submarines, navies gain a quiet network of machines designed to hide, adapt, and dominate the depths. But can it take on the most menacing peril in the ocean? No matter what design you are taking on, you need reliable parts. That's why engineers trust Mouser Electronics. The Carlo Gavazzi EM270 Series is a multi-channel power and energy analyzer designed for precise monitoring in single and three-phase electrical systems. Supporting input voltages from 160 volts to 415 volts and currents up to 630 amps, it delivers accurate insight across a 45 to 65 Hz frequency range. The DIN rail mountable design simplifies panel integration, while the onboard LCD display provides clear, at-a-glance measurements. With RS-485 communication for system connectivity and IP20, IP40 protection, the Carlo Gavazzi EM270 is well suited for industrial energy monitoring, load analysis, and power quality management applications. Check out the series today by visiting Mouser.com or by clicking the link below. From close enough to exact control, David shows the difference feedback makes.
Thanks, Andy. The simplest way to be able to control motors is just supply them with electricity. We can change the pulse width modulation on a DC motor, we can change the frequency that's going to an AC motor, but that's the simplest way to control a motor. The only problem is we have no idea whether the motor is actually responding the way it's supposed to. For this, we use a concept called closed-loop motor control. Most often, we see all the devices wrapped together in what's called a servo motor. A servo motor has both the motor itself, can be a DC or an AC motor, but it also usually has an encoder attached to it, which can track how fast the motor is rotating or what position the motor has rotated to. A closed-loop motor controller, therefore, has a lot more inputs and outputs. The inputs come from a controller that can do all the calculations of where do we need it to go, how fast do we need it to go. But it also has inputs coming back from the encoder of the motor to track its position and speed. The outputs go to the motor directly, just like any typical DC or AC motor. So these types of servo motors, or this closed-loop motor control principle, gives us way more precise control to be sure that not only are we sending the signals, but that the devices are responding the way that they're actually supposed to. Andy, back to you.
Thank you, David. All right, it's time to adjust your knowledge gains in our Smart Bid quiz with our 3 control automation questions. The questions are scored using actuator output percentage, and today we'll be testing your knowledge on robot grippers. Let's begin with our first question for 25%. A soft robotic gripper with embedded force sensors must pick up a tomato while following a predefined trajectory. During initial tests, the arm oscillates slightly when approaching the object. Which control adjustment most directly mitigates this issue? Is it A, increase the trajectory's proportional gain, or P, in Cartesian space? Or B, Introduce an impedance control layer that modulates gripper force based on object compliance. And the answer is B. Introduce an impedance control layer. Purely increasing P can reduce tracking error, but may amplify oscillations due to interaction forces. Impedance control allows the gripper to dynamically adjust stiffness and damping, accommodating object compliance while stabilizing motion. Okay, let's move on to our next gripper question, worth 25%. A high-speed suction gripper picks up thin metal sheets in a factory with strong cross drafts. Sheets occasionally detach mid-transport. Which adjustment improves reliability without slowing the pick and place cycle? Is it A, increase suction force and rely on open loop positioning? Or B, add closed loop vacuum pressure control with real-time position feedback? And the answer is B, add closed loop vacuum pressure control. Open loop suction may over or under apply force in fluctuating conditions. Closed loop control senses actual vacuum pressure and adjusts in real time, maintaining grip while allowing high-speed motion. Okay, let's go on to our last question, worth 50%. A robot must handle ferromagnetic parts of varying thickness. Using a permanent magnet gripper, thin parts sometimes snap or misalign during pickup. Which approach reduces this risk? Is it A, switch to a compliant force-sensing gripper that actively modulates grasp force? Or B, rely on faster approach speed to minimize interaction time? And the answer is A, switch to a compliant force-sensing gripper. Permanent magnets cannot modulate attachment force, causing uncontrolled impact on thin parts. Compliant force-sensing grippers dynamically adjust force and absorb shocks, reducing misalignment and part damage. Want to try again? Just click the link on your screen and be sure to check out our other AE videos for the latest in control automation.